Okay, so in this part we arrived to the most important theorem in the class. It's really worthwhile to take your time, take your sweet time, pause as many times as you want and rewind and absorb this main theorem, which again we will provide it without proof. I may illustrate it a little bit before we move on with other examples. But again, whatever follows from this lecture basically deals with this theorem in one form or another. So this gives you the main theorem of how to approach any linear ODE, even systems of ODEs, as you'll see later, but any linear, not necessarily homogeneous ODE. So suppose you have a linear ODE, again, L of y is just the linear operator, that linear combination in y, y prime, y double prime, and so on. And then on the right-hand side, you may have, like I said, a term which doesn't depend on t, the so-called non-homogeneous term, f of t. So this theorem simply states that to solve the original problem, to solve the linear ODE, you need to provide the general solution of its homogeneous part. By that I mean you take the associated problem by dropping f of t temporarily, right? So I mean you look at the equation as if it's homogeneous. So you ignore f of t for a while and then try to solve completely this homogeneous part. And you know already how many solutions you need to provide. Remember, that's from a vector space, so depending on the order of that equation, you may need to provide one, two, or more independent solutions. But bottom line, one needs to solve completely the homogeneous part to find the general solution of that homogeneous part. If that is achieved, then you only need a particular solution of the original problem. This may seem like a circle reasoning because what you're saying is that to solve L of y equals f of t, I need to provide a solution of the same thing. But remember, here we're looking for the general solution, so the description of all the solutions of the ODE. And as part of the method of doing that, we need to find, by any means possible, just one particular solution. And that may not be as hard as you may think in many cases. So you need a technique for solving the homogeneous part. You need a technique to solve the non-homogeneous part, I mean to find a particular solution of the non-homogeneous part. Both steps can be easy or hard depending on the type of the problem. So I'm going to illustrate this theorem, which is also called the two-step method, with a very simple example that you already know how to handle based on what we discussed so far. So this theorem basically suggests an approach called the two-step method of solving a linear ODE. So in the first step, you find y sub h, the solution, the general solution of the homogeneous part, L of y equals 0. And so you denote this part of the solution yh because, again, it doesn't represent the full solution, but just the homogeneous part of the equation. And then the second step, of course, is to find a particular solution yp of the original problem. And if you're done with these two steps, of course, you provide the general solution of L of y equals f of t as being the sum of the two, yh plus yp. So, as I said before, in some cases this is actually quite easy. And here's the easiest, perhaps the easiest type of ODE you're going to study in this class. The first order ODE with constant coefficients. And try to remember some of the concepts we talked about before. So let's say y prime plus 4y equals 8. Right? So a first order ODE with constant coefficients. Linear, non-homogeneous, right? It's non-homogeneous because you have this term on the right-hand side, 8, and it's linear. So what is the homogeneous part? So what is the first step in the two-step method? Well, you drop 8 temporarily, and you obtain the homogeneous part of the equation. Once again, you guys remember, I asked you to memorize the exponential ODE. So make sure you recognize whenever it appears, right? So I can write this as y prime equals a constant times y if you move 4y over. You could do this in your mind later once you get the hang of it. And I recognize this is an exponential ODE. I can do separation of variables, but remember, you're far better off if you just memorize it. So the solution of this, the general solution of this, is c to the minus 40. So that will be the general solution, not of the original problem that I'm trying to solve over here, but just the homogeneous part of the problem. Okay, so we achieved the first step. Now the second step. What is the what is a particular solution? So again, this can be easy or a hard question. We may actually have a dedicated, you'll see later, section on just how to provide that particular solution. But in this particular case, if you look carefully, you will notice that the equation admits a constant solution. So some solutions, if they exist, they are very easy to find. And perhaps the easiest type of solution that you can find is a constant solution if the equation admits a constant solution. And it always does if you have constant coefficients. So if you have no t appearing in the equation, you're guaranteed to have a constant solution. Well, most of the time. I mean, there are examples when that won't work, but in this case, it will always work. I mean, you always have a constant solution. So if you suspect that the equation may have a constant solution, let's say a, it's very easy to find, because if I plug in that magical constant into the equation, well, the derivative of a constant, remember, is 0. And then it's just a matter of solving for that constant to figure out the one that fits. So 4a equals 8, a equals 2. And again, try to do this in your mind, because it's very easy to do that. So if I plug in a constant, y prime is 0. So then what's left gives me a way to find that constant. 4y equals 8, y equals 2. If you need to, you can make this substitution, but I hope it's pretty clear that a particular solution can be found in the form of a constant, which in this case it's 2. So the two steps are done. The final solution, the full solution of the original problem, will be the sum of the homogeneous part plus the particular solution, which in my case it's c to the minus 4t plus 2. So exercise quite a lot with these examples, because this is the easiest way to practice the two-step method. Namely, when you have a constant first order linear ODE with constant coefficients. So here's another example. Let's say I have 4y prime minus 6y equals, let's make it with nice numbers as well, let's say equals 18. So what is the homogeneous part of the equation? Well, that's 4y prime minus 6y equals 0. Again, I can recognize this as an exponential ODE. You may have to do some algebra, right? So I mean, move the 6y on the right hand side. I can divide by 4 and simplify a little. 6 over 4 is 3 over 2. Once again, this is an exponential ODE. Y prime equals ky, right? So the homogeneous part of the equation is c e to the 3 over 2 times t, 3t over 2. What about a particular solution? Again, it happens to be a constant. If I plug in a constant for y prime is 0, the constant is 0, so therefore minus 6y equals 18, that's minus 3. So the constant solution is minus 3, or yp equals minus 3. And then finally, the full solution of the ODE is the homogeneous part, c e to the 3t over 2 minus 3, plus the particular solution, which is minus 3. So it's important, of course, to not confuse these situations with equations that don't have constant coefficients, because in that case it's not as easy as it is in this case. Even in those cases, though, you could still, by inspection, look carefully and kind of guess what the solution is. Here's an example of that type. So suppose you have y prime plus y equals 2e to the t. So the homogeneous part, again, it's as easy as before, right? If you drop the non-homogeneous term, you get y prime plus y equals 0, which is again exponential. Move the y over. So the homogeneous part of the equation of the solution is yhc to the minus t. But if you look at the particular solution, things are not as clear-cut. So first of all, this doesn't admit a constant solution. I mean, it's very easy to see, right? If I plug in a constant, y prime is 0, y becomes a constant, but that won't be equal to 2e to the t. E to the t is not a constant. This will not have a constant solution. So no constant solution. All right, so then how do you find a particular solution? Well, you pray, right? Well, it's not that like that. Good news is that actually we're going to learn later a method of actually finding a particular solution. That sometimes is a little bit lengthy, right? I mean, in many cases, if you spend a minute or so, you could actually guess it. I mean, think about this. If I have to obtain e to the t via differentiation, and knowing that e to the t remains the same if I differentiate it, it's not hard to guess that y should be some constant e to the t, because it will remain e to the t, and somehow the sum of the two should give me 2e to the t. So if you come up with this approach in your mind, you will realize that the particular solution should be e to the t times a constant, which in this case is just 1, right? Because when I plug in e to the t into the left-hand side, e to the t prime plus e to the t, that's obviously 2e to the t. That's out of range. So 2e to the t, like that. So sometimes you could just basically find that particular solution by inspection, if you're lucky. If not, if you cannot find it in a minute or so, just use the more advanced method that you're going to learn in the class. So, but for now, the full solution of this will be c to the minus t plus 2e to the t. Remember also that we may have, in many problems, initial conditions. So as with all differential equations, the initial condition is dealt with at the end of the problem. So let's say in this particular case, the problem stated here was accompanied by an initial condition. Let's say y of 0 equals 5. Nothing special about it. Again, once you're done with the full solution, you're going to impose that initial condition at the end. Just make sure you don't impose it on a portion of the solution. Sometimes people try to find c by using the initial condition right here. Remember, yh is not the full solution of the original problem, but this is the full solution. So y of 0 equals 5. That means c times e to the 0 plus 2e to the 0 equals 5. And that gives me c equals 5 minus 2, which is 3. And then finally, the exact solution of the initial value problem will be 3e to the minus t plus 2e to the t. So at this point, you have all you need to approach the homework. Again, make sure you understand well all this lecture before you actually attempt the homework. It's not that difficult. In some cases, the problems will mention the particular solution, and you have to do just the first part. And in the next lecture, we're going to learn how to actually solve by a formula any first-order linear ODE. Now, before we call it a day, let me just mention briefly, for your own knowledge, why actually this theorem looks the way it is. I mean, why, in fact, why the two-step method works, right? I mean, when you have non-homogeneous equation. So in particular, why that's connected to the homogeneous part. So I'm going to actually give you just a brief argument right here, so I don't have to erase the whole thing. One thing to keep in mind is that if you have a linear ODE, and so this portion actually you don't have to write it in your notes, just take a look at this. If you have a non-linear ODE, a linear ODE, because remember, we can distribute this linear operator. if you actually come up with two solutions, so imagine you have two solutions of this problem, y1 and y2. So that means L of y1 is f of t, L of y2 is f of t. So imagine you have two solutions, again, of the original problem, linear non-homogeneous. Notice what happens if I actually plug in for y the difference of these two solutions. So let's say I plug in the difference between y1 and y2. That means I stick in into y the difference between y1 and y2. Now remember, this is a linear in y double prime and so on. So you can distribute the derivative sign. That means the entire linear operator can be distributed and rearranged. In the previous part of the lecture we did something like that. When I checked that c1y1 plus c2y2 is a solution, I did something like that, right? I mean, I just distributed the derivatives and I rearrange the terms so that I can collect the y1s and y2s together. But I'll notice that if these ones are solutions of the same problem, L of y1 is f of t, L of y2 is also f of t. So that means the difference between any two solutions of the non-homogeneous problem is a solution of the homogeneous problem. That is the whole key of the matter here, because that means you can always relate any two solutions via a solution of the homogeneous part. So this is not a sleight of hand, right? I mean, you just add and subtract the same thing, right? So I mean, you can relate a solution with another solution and the solution of the homogeneous part. Alright, so that means if I manage to find the full homogeneous part of the solution, it's what we called YH, right, in the previous examples. So if I manage to solve completely the homogeneous part, that's why I need only a particular solution. Doesn't matter what solution. Doesn't matter which particular solution you're lucky to find, as long as you solve completely the homogeneous part. This describes any other solution of the problem. Because, I mean, this is the mystery sometimes. I mean, how come it's just enough to find a particular solution? Whether it's a constant, like in this example, or maybe a nice function that fits here, like e to the t, how come it doesn't matter which particular solution you pick? And it doesn't, because the homogeneous part of the solution, if you solve it completely, covers the difference of any two solutions of the original problem. So again, the key thing is to be able to solve the homogeneous part completely. Then you only need a particular solution to solve the full problem. So from this point on, I would like you to basically think of this as a mantra for the class. Linear equations or systems require in general two steps: solving completely the homogeneous part, just finding a particular solution by inspection, by looking carefully, also inspection, or by applying other means you're going to learn later in the class. And then, of course, the full solution is the sum of the two, always, always. So, I mean, if you look at the solution of the linear ODE, you will always be able to identify the two components. The one with the constant of integration c, that's going to be the homogeneous part. The remaining is the particular solution. So, that's it for today. I'll see you later.